Okay. How many of you here? We got 12 here. Is it correct? We got 12. No, we got 11 here, minus me. So 11, 12, 13, 14, 15, 16. 16.
One coming late 17, so 3 people missing.
3 people missing. 1 in Dubai, I think. So 1 in hospital.
Yeah.
For 1 girl. So very sick. Yeah.
Yeah, so 2 people.
Yeah, she said it was very sick. So hopefully nothing bad. Okay, let's start. Yeah, now it's already 8:10. Okay, let's start. So today we combine 2 practical. Can you hear me right?
Yes.
Yeah. Okay. So today we combine practical 2 and 3 together because we are using the ball and stick models. Okay, come. No, say that. Forgotten social distance. Okay. Yeah. So you can see over here, there are a lot of ball and sticks over here. So today we combine practical 2 and 3. So everyone have the chance to do the ball and stick because we got more than enough. Okay. So today we're going to do the modeling. Okay, practical 2 basically is the modeling for the alkanes, alkynes. Okay, so looking at the 3 dimensions, because usually in the lecture as well as in the tutorials as well, in the writing as well, all those. Okay, basically we are drawing, right? We are drawing in the 2-dimensional structures. So today you can actually build a 3D models, okay, and look at the overall 3D structures, so that you can know like what is staggered, what is eclipse structure, okay, where is things, okay, how much space they actually take for the whole structure, okay, whether is there a steric hindrance and so forth. So you can feel that. And also you can demonstrate the rotation of the bond. Later you can see the rotation of the bond, yeah. So for the alkenes, you actually can rotate the bonds, okay. So you can see from here. So I got a lot of ball and sticks. So you can see if there's a single bond, it can rotate. That's why you got staggered eclipse, okay. But if you got something like that, yeah, later you can do it. Just demo. 1, 2, 3, 4. Okay, you have something like a double bond or maybe a ring structure. Okay, either double bond or ring structure. There you go. 1 more percent. Oh. Okay, double bond or ring structure. What happened is that, oh, you got restriction. You cannot move. See, cannot rotate. So if you cannot rotate, what happened? You got cis and trans conformation. Okay, cis and trans. So in this occasion, you can see that it's all block. Okay, so you can do nicely. It's all block. Okay, so they cannot rotate. Cannot rotate means you got cis and trans. So in this case, you can either have a double bond or you can have the ring structure. Okay, a ring structure, same thing, even though it's a single bond, but then it's a ring structure. Okay, there's also a restriction and rotation, which means it's a cis and trans. You got cis and trans conformation. Okay, whereas you got a single bond, then you can rotate, then you can have staggered or eclipse. Okay, so that is for practical 2. Practical 3, this week we are going to talk about the stereoisomers. So this Wednesday we're going to talk about stereoisomers. So you can look at some of the things now, okay, today. So stereoisomers, basically they have the same molecular formula. Okay, they got the same molecular formula. Then same atom attachment, which means that the carbon attached exactly the same thing. Just that later on we'll build Okay, what you build, right, is that they have a different orientation only. Okay, they look almost the same, but just that one is up, one is down, which means that the one of the atoms, right, is opposite switch already. Okay, later on they will demonstrate as well here. Yeah. So how you can draw one of the things that stereoisomers, right? So there are a few different types of stereoisomers that you see. There is enantiomers. Okay, enantiomers basically they have a same molecular formula. Okay, same atom attachments but different of the orientations. And one of the feature, right, is that they are mirror image. Okay, they are mirror image, but the special type of mirror image, they are non-superimposable mirror image. Okay, non-superimposable means that they cannot stack each other. Later you'll see. Okay, so they are exactly the same. You basically what you can do, right, is you can build another. So you want to know whether is it superimposed, whether is it an enantiomers. What you can do, right, is that you build a model already. Okay, then after that at the mirror, you put the molecule in front. Okay, you put the molecule in front, and then you build the model inside in the mirror. Okay, so you build. Later on, when you compare these two molecules, they are non-superimposable, and they are also a mirror image. They are non-superimposable, which means that no matter how you stack, they cannot superimpose, just like your hand like that. No matter what, you cannot superimpose. So you see, this is a mirror. If I put my hand over here, right, with the mirror, okay, so this is going to be the molecule. Okay, and they cannot stack. No matter you say, sir, I can stack on it, right? Cannot. Here is the inside, here is the outside. How to stack? It's wrong thing. Unless I switch all these fingers around, then I can stack. Okay, because the outside and outside, inside and inside. Okay, so that is one thing you can see from there. Then diastereomers, they are not mirror image. Okay, so there are a few different type of the stereoisomers. Okay, later you will see as well. Okay, in the practicals. Okay, so there's one they talk about stereo centers. Okay, stereo centers is also chiral carbon. Yeah, CHIRAL chiral. CHIRAL chiral carbon. Yeah, stereo center. Okay, if later you see the word stereo center, STEREO. Okay, stereo center, CENTR. Stereo, STEREO, CENTR, stereo center. Or in the lecture, we'll call it as a chiral carbon, CHIRAL CARBON. Okay. Okay, I repeat again. Yeah. Later on, you will see stereo center inside. Okay, how you spell stereo center is STEREO CENTER. Stereo center. Just write down stereo center. STEREO CENTER. Okay, stereo center is also what we know as chiral carbon. CHIRAL. Okay, CHIRAL CEN. No, carbon. CARBON. Okay, stereo center is also chiral carbon. Yeah. Okay. Basically, chiral carbon. How you know whether is it a chiral carbon? As long as there are 4 different things attached to it, then it's a chiral carbon. Okay, 4 different things attached to it is chiral carbon. Okay, later you will see as well in the practical. Okay, all right. So any questions from inside? So these are the 2 things we're going to do: build 3D models. Yeah. Any questions? Today, who can I use as model? Nick. Okay. Okay. Any questions? No question? Sorry? CHIRAL. Chiral carbon. Chiral carbon, or also what we call stereo center. Oh, one more thing before you guys finish start there. Okay, please remember to treat it gentle. Okay, because the head that holds the pin, right? You can either break the pin or you can crack the hole here. Okay, so I have to be careful. Again, be careful of the pin, because if you too harsh, you might break the pin up inside here, okay, and not usable anymore. And for the carbon, right? For the carbon, please choose the one with the four different with the four spoke. Okay, there is one that is 5 spoke. Okay, there's one that is 5 spoke. 1, 2, 3, 4. This one. You can see. Oops. Oh, very bouncy. Okay, so you can see from here 1, 2, 1, 2, 3, 4. Okay, 4 spoke only. Okay, use this one, 4 spoke. Don't use this one. This one got 5. 1, 2, 3, 4, 5. Okay, 5 spoke. 5 spoke is a different thing. Carbon got 4 things attached with it. That's why I say 4 things attached to a carbon. That's why I use this as a carbon, not the 5 one. Okay, am I clear? If suddenly your structure very big, right, means that you use the wrong one. Okay, because only got 4 different things attached to it. And then in the practical, right, they ask you to use a certain color to represent like nitrogen, okay, or whatever. Okay, don't worry about it. Okay, don't worry about it. Directly use whatever color you have, because it's a different type of ball and stick models, okay, in there. All right, so just use whatever, because some I think is either lost or not sufficient. Okay, just use whatever you have. You just need to know in the practical inside. Okay, when you draw it out, just note that what color is what. Okay, that's it. Okay, so again, practical 2 and 3, okay, which is today, it will be for practice only. Okay, nothing to submit. So just draw. Make sure you know how to draw. Okay, and then you can visualize. That's the most important for this practical. All right, can yeah? Okay, all right, let's start. Okay. You see me? Okay, I go prepare for the what do you call it? The attendance. Hello. I will use it. Okay,
That's
for
why
today,
I
the
cannot find.
today class is 66x 4HP. 66x 4HP. Then for the class today is 66866x. X, yeah. 66x 4HP. All capital. 66x 4HP.
I think.
Okay, anyone here ever count the attendance? Anyone? Everyone done?
I think everyone does.
Everyone done here?
Yeah.
Inside? Who ever mark the attendance? Who ever mark the attendance? Yeah, like here. One more. Who is the one having attendance? Okay. One more person who is the one having marked the attendance. I think that you are like this.
Answer the question below the paper.
Someone on their Zoom and then left.
Those things for the trilogy, the test exam structure.
All the practicals are in the practical menu. Yeah.
Structure.
Okay, so here I think you do that.
I'm not
Okay, so this is the times. Times over here. Okay, how's it? Please do not see here. So do not see here means my screen. Okay, so first one, what are you doing?
The 1E.
1E, 1E.
Practical 2.
Okay, practical 2, 1E. Okay, for practical 2, 1A is what? With the model resting on the tree, examine the structure. Methane. Okay, so the first one is build a methane. So Nick, you can see here there's a methane over here. Okay, so this is a nice methane with hydrogen and carbon and then 4 sticks over here. So this one is basically the 3D structure. Okay, so the first one is that move the structure so that a different set of 3 hydrogen are on the desk each time. Is there any difference between the way the two structure look? Okay, so okay, so no matter how you oh, I touch your model. Okay, so you can see no matter how they turn around, okay, it's the same. Okay, it's the same. So 1A is like there's no difference. All right, regardless of what, it's going to be the same. Okay, fill the model so that only 2 hydrogen are in contact with the base, and press the flag. Draw the way in which the methane molecule would look into 3 in the 2 dimensions. So usually this is a 3-dimensional structure, right? Okay, 3-dimensional structure. So now you're trying to imagine, right, that you actually push it down to become a 2D structure. So a way for you to do, right, is that you can do it like this, in this way. Okay, so that imagine this is a table. So okay, so imagine this is a table. All right. So what do you see? No matter what I'm talking. Okay. Imagine the table. What do you see?
2D vision.
2D vision.
So like this.
Okay. So this is a 2D version. Yeah. So you can see over here. All right. So usually we draw what? A carbon in the center, and then the 4 hydrogen around it. Okay. So this is how you draw it. Okay. Using a protractor, measure the angle HCH on the model. What is a protractor? There you go. Here's a protractor. Okay, how do you, Nick, how do you measure? I'm telling you all the answers. Okay, they don't know what is going on. Actually, Nick, it should be that size so I can show to them and also show to the video. Like this. So how do you measure? Okay, so how you should do, right? You put this in the middle into the center. This the middle dot of this go to the center. Go further in. Go for this middle dot here. Yeah. This dot. Go in all the way in. Okay, in the middle. Okay, so make sure that for the protractor, yeah. Stick on there. So make sure the protractor, okay, you can see from here. Okay, the middle dot here. Okay, so use that and center with the middle of the carbon. Okay, so center of the middle of the carbon, very important. Okay, so what's the angle?
The angle is 110.
110, yeah, around about that. Yeah, sometimes 110, 119 is it? If you based on textbook, I think. Yeah, about 110 to 115 like that. Yeah, I think around that. Yeah. If you look at the lecture, right, you should stick over there. Yeah. Okay. The reason why this one is not so accurate is because sometimes this thing can be bent. Yeah. Okay, so I just show you guys. Okay, just right there now. I think it's 120, is it? 1, 3, 360, 130, 20, yeah, around about that. Okay, so what you do, right, is that you align one of it. So just say that you want to align this one. Okay, so put this in the middle, and one of the line here align with the carbon. So you see for here lah, what is it? Yeah. Okay, can see. Yeah, in this case, around about 120. Yeah, how about 120? Okay. Okay, so that is the angle. So you guys get it also, right? Make sure the center here, yeah, is in the middle of the carbon. Okay. Okay, number 2, construct. Hey, where were you?
Finish already.
Second one, okay. The second questions. Okay, so what you see over here, the second questions. Construct the molecules, ethanes. Okay, C2H6. Okay, note that you can make the ethane from methane model by removing the hydrogen. So you remove this one, the hydrogen, and then add 1 carbon in there. Okay, methane is what? Methane is 1 carbon, ethane is 2 carbons. Okay. This one is interesting. In this question 2, right, you'll be able to visualize staggered and eclipse. Yeah, staggered and eclipse. Okay, Newman projection. What is Newman projection? It's in the middle. It's in front of the practical introduction. Okay. Newman. Okay. So it's in the introduction here. You can see this is the Newman projection. Yeah. So you need to draw this Newman projection. Okay. So Newman projection can really see how it looks like. Yeah. Okay, for staggered and eclipse. Okay. Write the structural formula for ethane. So how do you write? Very simple, yeah. Very simple. Very simple. So basically, so you can see from here. Okay, same thing is how you want to write. Let's draw like that. So you got H is surrounding this side.
The 2D model, not the 3D model.
2D.
The way you see
2D, imagine you press it down. This way. So imagine you, yeah. So imagine you press it down. So you draw a C, H, 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 H. Okay. Yeah, correct, correct. Okay, draw a staggered or eclipse Newman projection of the ethane. Staggered or eclipse. How do you draw? Okay, so how do you visualize first? How do you visualize first? How do you visualize staggered and eclipse? Show me how you visualize. How you want to visualize staggered or eclipse? Which bond you want to see? Which bond is the one can be rotated for staggered eclipse? Which bond? Sorry? Yes, correct. This bond over here. Okay. Yes. So what is staggered? Which one is staggered? Show me. So what you need to do, right, is that your eye need to look from here. If you want for Newman projection, yeah, there you go. So you need to look from here. So need eye from here and look through here. Okay, so which one is staggered, which one is eclipse? See from there. Left side. See outside. Which one is eclipse?
I'm not sure.
I'm not sure. Okay. Turn my hand first. Oh, I touch on model. The one. I got virus to come to you. Okay. So you can see from here. What is this? So this is the bond that is got the freedom of rotation. Okay. So this is a single bond. Okay. Got the freedom of rotation. So it can rotate around. That's why it can rotate around freely. But then, as I mentioned in the lecture, right, one model is more preferred than the other one, which is the staggered. Right now, the staggered is the most preferred because the distance between the hydrogen is the furthest away. So, in order for you, if you want to observe this bond, okay, for the Newman projection, okay, since this is the one that is rotated, so your eyeball need to look through here. So you can see from here, look through here. Okay, see it. Okay, look through here. I see from the camera. Tell me to hold this paper. Yes, okay. All right. So what do you see? What model is this? What is this? Is it a stagger or eclipse? Is it a stagger or eclipse? Can you see the behind now? It's more or less blocked already, right? Right now, it's more or less blocked already. So this is a eclipse confirmation. Stagger is what?
If it's staggered, so you move it a little bit so there's like all in one.
You want to be more obvious?
Yeah. That one is staggered, right?
Yeah, this is staggered. So you can see all the hydrogen, all 6 hydrogen you can see from there.
Also, that is why the like the difference of measurement between one and another hydrogen is the same, yeah.
Different. Further away. This one is eclipse. This one is staggered. You can see that the distance from here to here is more further away.
Oh.
The front and back you can see further away. Okay, if I go from here, if I go here back, okay, to the eclipse model, right? You see, the distance is shorter.
Okay, I see.
Okay, and okay.
Can be staggered or the eclipse considered as cis trans or not? It's totally different with cis trans.
No cis trans. Cis trans only when there's a restriction in the bond rotation. Okay. Restriction bond rotation. Then cis. Okay. Okay, when there's a restriction in the bond, then got cis trans. This one no restriction at all. Can turn by itself, no restriction. This one no restriction, so no cis trans, either staggered or eclipse. Okay, how do you draw Newman projection? Okay, how to draw Newman projection? Newman projection, what you can do is draw a C, H, H, H. Then if it's for eclipse, you just draw side the side there.
So the extra link.
Okay, for the other one with staggered, right? Just draw like that. This one is only like to draw it out only. Okay.
So is it necessary to put the C?
Sorry?
Is it necessary to put the C
Which one? Where?
in the center?
Of course lah. If not, you don't know what is it.
Actually, here is
Huh?
a
Yeah, but you can draw a C there, no problem.
skeleton structure.
Yeah. Either way, that's fine actually. Yeah. But I normally draw a C where I know there is a carbon there. More clear lah. Okay. Yeah. Okay.
Okay, okay.
Okay, staggered eclipse confirmation. Okay, this is bond rotation. Yeah.
Nick,
Hey,
Nick, can you help us to take a photo of what Dr. Ben has drawn and put it on the group chat? Thank you in advance.
My front camera, not the resolution not very good. Cannot focus.
Yeah, if I'm taking the screenshot here, it's not too clear, so better for someone. Thank you, Nick.
right, no problem.
Okay, what's next? Next is butane. Oh, butane more what they call is more complex, yeah. So it's C4 H10. Since this is social distancing, so no partner. Only construct. Construct a model of butane. Butane is what? Butane is 4 carbon long, yeah. Okay, butane is 4 carbon long. And then adding the needed hydrogen. So you just take out one and then add on. First, orient the model in such a way the carbon appear as a straight line. Okay. Next, tilt the model so that the carbon appear as a zigzag. Draw each of this structure in 3A. Note that the structure you draw are for the same molecules, but represent a different orientation and projection. Okay, a 3D model, right? You can see how basically you can look in different ways. This is a 3D model, right? Okay, so depending on what ways you look at, right, you can sort of like represent. It's the same molecule, but it's a different representation. So you can draw differently. Okay, but it's the same molecule. Okay, this is how you what he's trying to say. 1, 2, 3, 4.
Oh, okay.
That's correct.
Then go here.
That's correct. Oh, you don't see from there. Own self construct. Butane is 4 carbon. Going to look at their book, yeah. Look at your manual. Okay. Where's your hydrogen? Go. Yeah, lazy to go, but then that's why you need to visualize. Okay, so you see from here, butane. Okay, butane. Butane is 4 carbon. So there are two ways you can look at it. So if you look at it, right, it says that it's tube, so that it's straight line. Another one is zigzag. So what is this? What is this? Zigzag. If you want to draw, you can draw like that, zigzag. C, zigzag. If I turn around, it's the same molecule. What do you see?
Straight.
Total, it's straight, right?
Yeah, there you go, straight line. I just turn around only. Zigzag. I just turn around. You see, it's straight line already. So it's all how you draw is C, and then H all around. Zigzag. Straight. Zigzag, straight. Okay?
Okay.
Make sure when you draw all the structure, include all the H here. Okay.
Oh, but we usually draw them in the straight position, right?
It's the same. Both is the same. Usually, if you want to be less confused, then draw it straight lah.
Okay.
Both is the same molecule. No problem. It's the way different way of drawing only. Okay. Yeah. Anyone? This is a zigzag. This is a straight line. Okay. One is zigzag, one is straight line. Okay. It's exactly the same molecule, just that you view it differently from different angles. Okay. Okay, done. Okay, B. Okay, next come. Side along the carbon-carbon bond of C2C3. So from this one, right? Okay, tell me which one is C1. C1. Okay. Need one to go this one C1, not instead of the other one. That's fine. Exactly the fine.
Oh, so
okay.
Doesn't
matter. Doesn't regardless which end because it's the same.
They have the same
Yeah. Yeah.
So
C1, C2, C3, C4. Okay. So which one is C2 and 4?
C2 and 4. This one and this one. Wait, sorry.
Sorry, C2 and C3.
C2 and
sorry, I say wrongly, not your fault. C2 and C3.
This one and this one.
Okay, C2 and C3 is this one and this one. Okay, so this one and this one. So the ask you to visualize along these two for the staggered and eclipse. Okay, so how do we do it? Draw a staggered Newman projection. Rotate the C2 carbon clockwise by 60 degrees. Draw the eclipse model. So how do you do? So if you want to do a Newman projection for this, so your eyeball need to go from here, exactly like how you are seeing now. Okay, seeing now. So what you can do, right, is that you can imagine. Okay, you can imagine this whole thing. Okay, this whole thing over here is CH3. So this whole thing over here is CH3, not H. Okay, so you just draw CH3. This one is CH3. Okay, So exactly same thing. So what you see from here, so don't look at it this so complex. Just look at this as a CH3. Imagine that this is a CH3. I want to make it less confused here. Imagine this is CH3. This one is CH3. Okay, CH3, CH3. So this is C2 and C3. Right not? So same thing lah. There you go. Eclipse. So you draw instead of H, you draw CH3. Okay. Okay, CH3, H, CH3, H. This one is an eclipse. 60 degrees is what? 60 degrees is like that. There you go. Very good. Okay, so we got CH3, H. Exactly same thing. Okay, exactly how you draw it, just that you draw it differently. Okay. Just draw CH3 only. Okay, just do. Okay, just change to CH3. And see here, CH3, CH3. CH3, here is CH3. So basically, you just change the H to CH3. Hey, social distance, right? Social distance. Yeah. Later, yeah. The guys are like all hugging each other. Social distance, please. Correct, no? Because the main thing is you want to see the C2, C3, correct not? So you just concentrate C2, C3, enough already lah. Then draw the other one is just write whatever there lah. If here is more complex, becomes C2H5 and C2H5 lah. Because you only concentrate C2 to C3 only. Okay, whatever is in this become a branch already. Okay, okay.
So Dr. Ben, actually it doesn't matter what is the part of the side one. We can like substitute the hydrogen with other thing, right?
Correct. Because in the manual it says that you focus on C2 to C3 . So whatever is the other side, you just draw something more complex as in you submerge together you merge together. Yeah, it can be C2H5, up to you. Yeah, depending on.
So actually there's no we can substitute the H thing, so the hydrogen thing. So it's basically based on what molecules we want to make, right?
Yes.
Okay.
Just imagine, just take out this one. Just take out this one easier. CH3. Yes. For simplicity lah. No, just the C. Just the H. For you to visualize easier. It's the H still there one. It's the 3. And the CH3, exactly how you see this one. Then you draw CH3, then H, then behind what is CH3, H3, then 60 degree, you just turn a bit only, and become become the second. Then what CH3? Because since they also the focus on C2 to C3. Okay. Let's see if there got Okay. And done. Okay, number 4. Number 4. Number 4 is C2H6O. Okay, with the oxygen. So there are 2 isomers with the molecular formula C2H6O. Okay, ethanol and dimethyl ether. Okay, construct both of these isomers. Draw these isomers and name each one. Okay, so how do you draw this? How do you do this one? This one is isomers, yeah. Okay, it's more or less it will be overlap with the practical tree. Okay, isomers. So isomers are basically they have the, in this case, right, the is with the same molecular formula but different atom of attachment, which means that the atom attached differently. Okay, so this one is different from the one that we're going to do later on. Okay, stereoisomers, which is basically they are enantiomers and so forth. Yeah, it's different. Yeah, okay, because the other one is they have the same atom attachment. Yeah. Okay, so let's do this one. So how do you draw ethanol? How do you make ethanol? There you go. Oh, OH. This is what? This is ethanol. CH2OH. Okay, draw the other one. I make the other one. So you can see from here, ethanol. CCHHH. This one is OH. Dot like that. Okay.
Then can you make the molecule, the oxygen is on the middle?
Sorry?
Can the oxygen is put on the middle between those C?
That's the other one. That's a dimethyl ether. This one is ethanol. Yeah, with the OH at the behind one. Okay. Okay, so this is ethanol. Okay, dimethyl ether. Okay, there you go. Okay, so this is dimethyl ether. So you got 2 metal here. One metal, okay, CH3, another metal, CH3. Okay, so this is a dimethyl ether. Let's see it. Yeah, dimethyl ether. Okay, and ethanol.
Because
Yes.
the ethanol, I mean the alcohol bond need OH, right, to be
Yeah,
together.
Alright, okay. Here got lone pair. Here should have lone pair. That's why it bend down.
Oh, okay, okay.
Later you will learn this from the alcohol chapter. Okay.
Okay.
Lone pair here, yeah, guys. What is lone pair? Lone pair electron is basically an electron that is not paired to anything, so it's surrounding here. So you push the hydrogen down. Okay. Same goes to this one. Why is it bend down? Lone pair electron here. Two electron here. Okay, that's why it bend down. Okay. So two electron here. Okay, two electron, that's why it bend down. Okay. So you want to demonstrate, right? Of this one, same molecular formula. What does it mean by same molecular formula? How many oxygen? One oxygen. How many carbon? Two carbon. How many hydrogen? 1, 2, 3, 4, 5, 6. So it's C2H6O. Alright? This one, same thing as well. How many carbon? 2. How many oxygen? 1. How many hydrogen? 1, 2, 3, 4, 5, 6. So also C2H6O. Same thing. So these two have the same molecular formula, which is C2H6O. Okay, same molecular formula, same thing. But the thing is different, right? Is that they got different attachment. This one with the oxygen attached to the middle, this one oxygen attached to the end of the molecule. Okay, end of the carbon. So that is the main difference. Okay, and these two, since they have the same molecular formula, different attachment is called stereoisomer. Yeah, you got stereoisomers. Okay, sorry, not stereo, it's called isomers. Yeah, it's called isomers. ISOMER. Okay, stereoisomers is a different thing. Yeah. Okay, so these are two isomers. Isomers. Okay, not stereoisomers. Yeah, isomers. Yeah, ISOMERS. These two are isomers, okay, since they got same molecular formula but different atomic attachment. Okay, so you just draw, very simple. CH in the middle, okay. You can draw straight line, you can draw like curve, no problem. It's the same thing. Yeah.
Can the dimethyl ether considered as alcohol?
No, cannot.
There is no the OH bonding.
OH is not alcohol. It's ether. It's different thing.
Yeah, so it's cannot called as alcohol, right?
Oh no. Did I write alcohol? No. Methyl ether. It's an ether.
But
you won't be learning the what's it called? This group.
but actually the name of that, it's the same C2 how many H, yeah? And one
Okay.
O, right?
What's the formula? You mean C2H6O, is it?
Yes.
And what is molecular formula? It's not formula. You only
So
name the formula.
it's got the same molecular formula, but it's different in the name one.
It's different in the structure. The structural formula is different.
we got the same number of O, the same number of H, and the same number of C or not?
Yeah. Wow, your ball very bouncy. Oh, there you go.
Same molecule. Ah, I see, I see.
The structure is different. That's why it's very important that's why molecular formula, that's why I say, remember the chapter 3, I mentioned that when you want to condense down, don't lose the structural formula. Okay, so don't condense it.
The structure one is the one that we write like the bonding one, right? So we written down the bonding one.
Yeah,
Is it
structural formula is this one, no?
the CH after that strip CH again like that?
I think you want playing ball.
No. Mine got no name.
Yeah,
Structural
that one.
Yeah, so the molecular formula, it doesn't show all the structure at all.
Yeah. The structure one is the one that we write the bond, right? CH strip and then CH again like that, right?
This one is structural formula.
Oh yeah, right. I found.
That's why,
I see
that's
it.
why
I
it's
see
very
it.
important. You don't condense all the way. Some people, they condense this all the way to become molecular formula. They lost the structural formula. So you don't know what molecule is that already.
Yeah,
So
yeah.
don't over condense it.
Oh, this would be CH3CH3. CH. Yeah. I think it's CH3.
Oh yeah, CH3. Yeah. Error, yeah. I don't know why it lost. What is it? Yeah, it's CH3, yeah. It's CH3 is that, not CH3.
Oh yeah, okay.
Okay, buttenes. If a spring are available, which in this case you don't have spring, so what do you have? You have the oh, there you go. Nick already done already. Okay, so in this case, there are two isomers from cis. So you got cis and trans. Okay, so you got cis and trans. Trans. Okay, so you got cis and trans. So what you can do, right, is that you can twist a bit. I see, twist a bit looks nicer already. This one more. It's the same thing. You can do the other way also. So I just twist a bit. You can see more clearly already. Okay, so this is the double bond. Okay, which you cannot rotate. You cannot rotate. Okay. All right. If I can rotate only when I break the bond. Yeah. Okay. So I don't want to demonstrate that. If not, the lab officer is looking at me now to break the bond. Okay. So I don't want to break the bond. Okay, so you can see over here, so it's a restrict of movement. You cannot move. So you got cis and trans. So you can just push a bit nicely a bit. Okay, so you got this. In this case, which one you should compare? So you should compare this carbon and this carbon, this carbon and this carbon. Okay, so this carbon, the first thing I have teach you before, you need to look at the priority. Correct or not? You need to look at the priority. So which one is more priority?
The one below. The one below, the one up. The hydrogen.
Very good. So in this case, how about this? Which one?
CH3.
CH3 got higher priority, right now. So both of these is what? Facing down. Right now. So both of these facing down. So this is a cis or trans.
It's
Very good. This is a cis conformation. Okay, this is a cis. Okay, so you draw this one, cis. Okay. The other one, if I switch this one,
will be trans, yeah. Okay.
very good. So again, determine if for this one, which one is priority? This one. Which one is priority? This one. So you're comparing this and this. So one is down, one is up. So it's a trans configuration. Okay. So draw the structure. Very simple. For cis and trans, I like to draw like sideways. Yeah. It sort of like what it looks better. Yeah. Yeah, just draw like that. Some people they like to draw like that. It's not wrong, you know. It's not wrong. Just that it's more difficult to like see cis and trans only. Yeah, this is not wrong. This is not wrong. This is not wrong. Just that it's more difficult to see only. Okay. So this is the one that you need to draw. Yeah. Okay, so you see over here. I like to draw like up and down like that in this way. Okay, so you can see cis. So cis trans. You can see cis. Okay, this is not wrong, yeah. This is not wrong. If you can draw like short way as well, just that it's more difficult to determine whether it's a cis or trans. So you just tilt a bit and then have one up here, one down here. It makes it easier. This one can extend further, no problem. If here is another C, for example, here you see this is not CH3, this is like C2H5, then you can extend, no problem. Okay, just draw like that. It's easier to see cis and trans. Yeah.
Okay.
So it's not parallel.
Kindly, Dr. Ben, kindly help. Maybe Nick can help us to take a picture for OneNote. Right. Thank you.
I think Nick can take picture of all his all the answer for you later on.
After I finish the first answer.
Oh yeah. Okay. Thank you.
Okay, we can do faster a bit. We are finishing practical 2 already. Okay, so we can finish faster. Oh, I scared later my handphone no battery again. Okay. Okay, can you twist and turn or rotate one model or another? The answer is no. Just now I already told you already, right? There's a restriction of movement, so you cannot turn. Okay. Because you say that because it's a double bond. If you want to explain further, right, then you just say that it's a double bond, and it doesn't have you cannot turn because of the restriction of rotation. Okay, must have this keyword there, restriction of rotation. That's why you cannot have a twist and turn. All right. So you can explain further. You say that if you want to turn, the only way is to break the double bond, which require a lot of energy. Yes. Okay, boot time. If spring are available, which in this case you don't have spring. Okay. Construct two butene. Okay, two butene. CH3, C, triple bond, C, CH3. Can you have a cis and trans isomer in this system? Okay. Should have. Correct. No.
I don't think so.
Should have. No, cannot have. Yeah. Okay. In this case, because it's a triple bond, right, and there's only one thing at the side each, so you do not have freedom of rotation. Yeah. No, you got no freedom of rotation, but then you cannot have cis and trans because there's nothing to compare. Okay. Later you see. Okay. Yeah, just choose that. Alright. Choose that one. No. Choose that one. Yeah. Turn up. Right. Put that. Yeah. Not enough. Yes. Turn. Won't break. No, turn. Yeah. Sorry. Take the white one. Yeah. Yes. Yes.
So become more restricted.
It's more restrict. Even though this one is a restrict or rotation, yeah. But okay, this one is there's a restriction or rotation as well. Okay. But the thing is that there's only one thing at the side, so nothing to compare. There's no cis and trans. Okay. So no cis and trans in this case, even though there is a restriction and rotation. This one is a restriction rotation, but no cis and trans. Because only one thing at the side there. Okay. Okay, so this is a restriction, also only one thing, nothing to compare. Sorry? Or which section? Can lah. Yeah. You see at the side there.
You exchange the H for
Yeah.
CH3.
Yes. So there's the system. Okay. Okay, practical 3. Okay, very simple.
So I have a question.
Yes, come.
Number 6. Do we explain it or just say no? There is no isomer.
Now you explain lah. You explain. You want to explain further? Is actually this practical is for your is for enhance the understanding. So you can explain further lah. There's no right and wrong. So you just explain further. Say yes. There's no cis and trans. Okay. Although there is a restriction or rotation. Okay. It's because at the side here you can say that there's only carbon, only one atoms only. So there's nothing to compare. Okay. So there's no cis and trans. You can explain further lah.
Oh, all right. Okay. Thank you.
Okay, practical 3. Yeah, toilet. Nick want to go toilet break. Is it okay?
Okay lah.
Okay. So there's only one carbon, so there is no what to compare. So,
There's no.
For the middle, there's
there's
no
no cis and trans.
all the cis and trans to compare.
Yeah.
Oh.
No, not to compare. No, there's no cis and trans.
That's no.
Construct a model consisting of tetrahedral carbon center with 4 different components attached. Okay. Red, white, blue, green, each color represent a different atoms. Okay, so as I mentioned before, you can have a different atoms here attached to it. Does this model have a plane of symmetry? Okay, a plane of symmetry can be described as a cutting a plane that when pressed down to a model object divides it into 2 equivalent halves. The element on one side of the plane are the exact reflection of the element on the other side. Okay. Alright, so we will wait for Nick to come back to construct it then. Alright. Okay. Yes. Okay. So is it no such funds? Is it just because of the structure?
For what, 6?
Yeah.
Yeah, there's no other chain at the side. So you can't really compare. There's some. It's carbon though.
And 7 tons of contaminated water. Wow. I'm not going to clean it. Huh? Last year was like one whole week I don't have water. This is like yearly routine. Not yearly, I think monthly. The day the other side no water. Last month. It's on the industry area there. Yesterday also didn't rain. I thought normally rain only will flush down. Okay, so Nick have came back from toilet. Okay, and he has constructed the carbon with 4 different things attached to it. You can see from here. Okay, so you can see there are 4 things attached to it. Okay, 4 different color. All right, 4 different color. Okay, so the question asks. Okay, so the question is asking. Does this model have a plane of symmetry? What is a plane of symmetry? So if you just say that I have a paper over here. Okay, if I fold it nicely. Okay, if I fold it nicely. Okay, so if I fold it nicely, right, then there's a plane of symmetry over here. So this one is the line of symmetry. Okay, so this is the line of symmetry. So this side is exactly same as this side, the dimension. Okay, if I fold it unevenly, right? Yes, then this one become not symmetry anymore. Okay, because I fold equally, the left side and the right side is exactly the same. That's why there's a plane, or this is the plane of symmetry. So the question is asking you, is there a plane of symmetry? So basically what you can do, right, you can chop this one in half. Okay, so chop this one in half. Either you want to do half here, no problem. Okay, either way is fine. Chop here, chop here, no problem. But regardless of what, there shouldn't be a plane of symmetry. The reason is because it's made of 4 different types of atoms attached to it. Okay, so even though you can chop over here, nice, here, half, nice, but here and here is 2 different things already. Okay, it consists of the same atom. Yeah, if you want, just say that you want the plane of symmetry, right? Then you can switch to this one. If yeah, one of these, this one. Okay. So if I do this one, yeah, there's a plane of symmetry because these two atoms is the same. So if I chop, okay, if I chop over here, then these two is a there's a plane of symmetry here. Okay, there's a plane of symmetry here if these two are the same. Okay. Okay, molecules without a plane of symmetry are chiral. Okay, in the model you construct in number 1, the tetrahedral carbons is the stereo center. Okay, stereo center, as I mentioned before, is chiral carbon. Yeah, so number 8 you can see from here. Okay, in the model you constructed in number 1, the tetrahedral complex is the stereo center chiral carbon. The molecule is chiral. Okay, so this one is the chiral carbon. Okay, this one is a chiral carbon. Carbon attached to 4 different things. Okay, so if you want to determine a chiral carbon, you need to determine one by one. If this molecule is more complex, there are more, then you need to determine one by one whether is this a chiral carbon. Okay, so these are 4 different things attached to it. It's called a chiral carbon. Yeah. Okay, so when there's a chiral carbon, usually this molecule is called a chiral molecule. Okay, chiral carbon, chiral molecule. Okay, so chiral carbon, this one holding is called chiral molecule. Okay, unless there's a plane of symmetry here. Okay, now take a model you constructed in number 1 and place it in front of the mirror. Construct the model of the image projected in the mirror. So Nick now is going to look through a mirror. Okay, if you see something like a black shadow behind, please don't look at that. Nick, yeah. Concentrate the molecule. Yeah, just leave it there. Just leave it there. Yeah. Is it here like that better? Your mirror very small. It's okay. Yeah. Okay, look at inside there and build the one inside. Okay, my turn to go toilet.
You can see a reflection.
Just answer like this.
Okay, I think so.
Wow.
I just answer yes or no.
I think you'll be fine, but you know, you put up, unless you know
see
the,
what happens. You put a mirror in front of it, you can see the reflection of the reflection image. Okay. Some of my confusing. Just like if you put a mirror in front of the camera for a Zoom call. What do you think about these?
You just see the camera only.
You see the camera, you see the reflection reflecting itself. You know, what do you think about it? Just wasting my time.
Sorry. It's just me. Okay. All right. Welcome. Welcome. Myself back. Okay. Look over here. So where are we? Yeah, in number 8, yeah, molecule without a plate are chiral in the molecule constructed tetrahedral. A simple test of molecule look at the serial 4 different type attached to it. Okay. Now take a model, construct the place in the mirror, construct the model. So Nick has constructed a model, okay, which is based on that mirror image. Okay, look very mirror image to me. Okay. So this one is the mirror image. So in reality, yeah, there are in this world, there is actually like 2 different type of molecules, yeah, and they are chiral to each other, which means that, but one maybe is more more abundant than the other, which means that they exist more than the other one. But they do exist, the other part, okay? So you can draw you can have 2 different types, you can visualize here. If one is the object, what is the other? Okay? Yeah, mirror image, or what we can say is a non-superimposable mirror image. Okay. There you go. Yeah, non-superimposable mirror image. Okay. Non-superimposable mirror image. All right. Do either have a plane of symmetry? There's no plane of symmetry. Are both chiral?
Yes.
Yes. Okay. Now try to superimpose one into another. Can you superimpose or not?
No.
Yeah. So how do you superimpose? There you go. Try to do this. Cannot. Okay. Like that cannot. Same but different. You do like that. Even cannot. Okay. So it means that it's non-superimposed. So superimposed means you just like stack with each other. You try to see whether cannot. Okay. In another one, 2 molecules that are. Yeah. Okay.
Yeah.
So actually, Dr. Ben, it can be superimposed or not?
Cannot.
Cannot, right? Because
So if you see over here.
Yeah.
What different?
Oh, okay.
See? Cannot. Two different. Can superimpose means that it's the same. They are mirror image and they can super. Later you will see also. Okay. There's one that is two. Even though you can build the mirror image, okay, because there's a plane of symmetry, that's why it can be superimposed. Okay.
Okay.
Yeah.
Sir.
Yes.
Sir.
Yes. Can you hear me?
Yes. If a molecule has plane of symmetry, we can assume that it also can be superimposed.
Where is it? Come again?
Is it correct to assume if a molecule has the line of symmetry, we can assume that it can be superimposed?
Depends actually. It's a case by case basis. You need to look at the molecule again.
Okay.
Yeah, that's why it's best, right? You don't make assumption and try and compare the molecule.
Okay.
It depends on, like, some molecules, right? Is special. Like later you see that one of the meso compound. Okay.
All right.
Yeah. Okay. Okay, so basically, if a stereoisomers, right, there's a band of light. Basically, in the lab, right, they have a machine, right, that can determine this. So they prepare the molecule. Just say that you dissolve all these molecules, right, okay, in one of the solution, okay, in one of the solution. So you dissolve inside already. Then you just place inside the machine, and then shine through a polarized light. So if the light pass through and then it rotates, okay, to the left or right, okay, they can bend the light. That it shows that is the molecule is either what we call the optically active. Okay, so it will bend either left or right. Okay, so which means that the molecule is optically active, and so is a current molecule. Okay, so there's a machine that in the lab that can do that. Okay, so just by dissolving the solution, the molecule in the solutions, then after you test it, then you bend left or right the light. Okay. Supernatural. Okay, mesoform. This is the one that I'm talking about. The molecule is no one. There's no plane of symmetry.
Oh, so you compare it by one, not both.
Both also don't have plane of
Both
symmetry.
of them
Oh,
Yeah, both also
because they don't have the same atom.
Oh,
So
I
we
thought
shouldn't.
I thought it was gonna be like that.
oh, like that? No.
Oh, so just
This is called mirror image.
oh, alright.
Non-superimposable mirror image.
Also, the answer for A is none.
Where is it called? A is what?
Oh, there's no plane of symmetry.
No, this one A is this one. Non-superimposable mirror image.
Oh, okay.
Yeah. Okay. B is do they have a plane of symmetry? No. Yeah. That's why it say written there either either have a plane. There's no. Both chiral, yes. Okay. Yeah.
Okay.
Yeah. Okay. B mesoform. Okay. Come, Nick. Can you build a tartaric acid? Yeah. Tartaric acid is very special. Yeah. Because the tartaric acid. Okay. For the tartaric acid, it's special in the case, right, is that if you look at this carbon, okay, if you look at this carbon, 4 different things attached to it. If you look at this carbon, also 4 different things attached to it. Okay, which means that this one is a chiral carbon, this is a chiral carbon. Okay, so by right, this molecule should be a chiral. But because of the plane of symmetry over here, there's a plane of symmetry here, which makes it, right, everything change already. Okay, so you can actually build the mirror image from here. But if you see, because of the plane of symmetry, right, these two molecules is become a superimposable mirror image here. Okay. Yeah, can. Any problem, please ask. Yeah.
Teacher Ben,
Yes.
I have a question. So if it chiral, it could be said that it is mirror and not superimposable. Is it?
Come again.
If
If it's a-
if it is chiral, it
Yeah.
won't be superimposable, but it is my mirroring with the other one.
Sorry, I don't get it. Come again.
I think let I check for the one here after this question. If I still don't get it, I will ask you again.
Okay. Okay. C H O H.
Dr. Ben,
Hmm.
can you explain on number 7? I can't really understand it.
Number 7. Can I understand? Correct. Number 7. Construct a model consisting of the ideal centers for your type. Does this model have a plane of
What's
symmetry?
the C double O H.
You're talking about this one, right?
Yes.
Yeah. So you're asking whether is there a plane of symmetry? There's no plane of symmetry. Because if you cut over here, so regardless of what, you cannot have a plane of symmetry because if you cut over here, okay, if you cut over here, what do you see? These two are already. There's no
Yep,
plane of
different attempts. Oh, okay. All right, I get it now.
same thing as well, cannot. So no
Correct.
matter if you try to cut, okay, there's no plane of symmetry, which means that the left and the side after you cut, right, left and the right side is not the same. Okay.
Okay. Thank you.
Can for OH.
COOH.
Actually, I'm not very sure about the side, but I'll see how to build this.
You drew for the H's.
I use this one.
C is what? This one is like that. COOH. COOH.
Okay.
See the double bond.
Double bond.
See,
It's not enough blue color.
never mind, just show one first.
So can we actually consider it a chiral carbon since it's bonded to carbon itself?
It's a chiral carbon.
Because it's a different molecule.
Yeah.
Like this entire part is different. Like this.
All the carbons are chiral carbon.
Oh,
No, not all. Yes, these two are chiral carbon.
but
Yeah, the middle two, C2, C3 is chiral carbon. Yeah. Right.
oh, okay. Oh, we consider it as a group, not the molecule itself.
But afterwards only you find the molecule. Yeah, you consider the carbon first. If for chiral carbon, usually there's a enantiomers. Yeah.
Let me check. Your H. Your H there and your OH. OH there.
History. You look at the chiral carbon first.
Chiral carbon.
Yeah. You look at the chiral carbon first. Then after that only look at the whole molecule.
Oh, okay.
Which means that if there's a chiral carbon, usually there's a enantiomers. Usually, yeah, it's possible. Which means that there's a possible there is a chiral carbon, chiral molecule.
Oh.
But when you look at the overall molecule at the time, right, there's actually a plane of symmetry. Which means the left side and the right side is the same. So in that case, even though they have a chiral carbon, but it's not a chiral molecule. Okay, that's what I mean. So you can see from here, this is a wonderful job creating this monster. Okay. I look like crap. Okay. Okay. Yeah. Interesting. If you're able to play this at time, you can Nick broke one of the stick.
Broke already.
No lah, just okay. So over here, you can see this is the molecule. Okay, tartaric acid. Tartaric acid is something special, yeah. Okay. So again, there are so many carbons, right? One by one, you can determine whether is it chiral carbon or not. So in this case, this is not a chiral carbon because only got 3 things attached to it. 1, 2, and 3. Okay. So this one is a chiral carbon. We got 4 things attached to it. 1. Okay. Okay. See 1. Okay. 2, 3, 4. 4 things attached to it. So this is a chiral carbon. Is this a chiral carbon? Yes, because 4 things attached. 1 thing, 2, 3, and 4. This one not a chiral carbon because 3 things attached to it. 1, 2, and only 3 things. So the chiral carbon is only these 2. All right, but the problem is that if you look at this, the left and the right side, okay, the left and the right side, there's actually a plane of symmetry. So if you cut over here, the left and the right is same, left and the right. So there's a plane of symmetry over here. Okay, so the question for that, is there a plane of symmetry? Yes, there is a plane of symmetry. Okay, even though, so you can say the next question, is it a chiral or achiral? So even though there is a chiral carbon in there, because of the plane of symmetry, so this is considered achiral, yeah, achiral. Okay, okay. Yes.
So this one is the previous one that I want to ask. So chiral mean it's asymmetric, right?
Yeah, yes, correct. Achiral means not. A is not.
Which the structure of the bonding is mirror image, right?
You can actually have a mirror image from this. You can actually build a mirror image.
And is it not? I mean, like chiral is not superimposed, right? Or it is superimposed? It's not, right?
Alright,
Chiral is cannot superimpose, right?
yes. Is no. Achiral is in this case is achiral because there's a superimposable mirror image. So if I build the mirror image, I borrow your. So if I build a mirror image, dropping out. I can actually build a mirror image out from here. I can actually build a mirror image out from here. The mirror image, right, will be okay. So if you build a mirror image, right, it's going to look like that. Okay. So I put a mirror in the middle here. Okay. Put a mirror here. These two are the mirror image. Okay. These two are the mirror image. But the thing is that it can be superimposed because if I just stack over here, even though it's mirror image, but it's superimposed. Okay. So this one is actually a superimposable mirror image. Superimposable mirror image. Okay. In other words, what do you see over here? When you are when it's a superimposable mirror image, what do you see over here? These two molecules is actually identical. Okay, these two actually is identical, which means that this is actually a same molecule. Even though you can build a mirror image, but these two are the same molecule. Okay, and there's a special name for this we call as a meso compound. Is it okay? Still confused?
I think I get it now.
Okay. Yeah. You first you build the direction.
I don't have now.
You just use any color you want to understand.
Then you can take for another one. Okay, so the question over here, use circle to indicate 4 different groups for carbon Ca. Okay, carbon A and the carbon B. Use a square for carbon B. Okay, so this is how you do it here. Okay. So for carbon A, okay, so it's 1 group, 2 group, 3 group, and 4 group, the whole thing. For square, you got for this carbon, you got square 1 group, 2 group, 3 group, and then 4 group. Okay. And this is how you do the 11, 11. Okay, number 11. Okay, project the model into a mirror and construct a model of the mirror image. Are these two models superimposable or non-superimposable? So just now I demonstrated already, model being constructed now, okay? But just now I showed that it's actually superimposable, okay? So the answer for 12 is superimposable because you can actually stack on each other. It's actually the same. Okay, are these models identical or different? They are identical, yeah. They are the same molecule. They are the same molecule for 12. Okay. Yeah, superimposable. Superimposable, not superimposable. Because that's how you got stack. And they are identical.
So
Yes. Say.
okay,
yeah.
what does it mean for the models to be identical in this case? Is it possible that the molecules are identical but non-superimposable?
No, they are the same molecule.
Like the previous case we discussed about, is it possible for the models to be identical but non-superimposable?
Identical and non-superimposable. Cannot be. They are the same molecule. How to be non-super?
All right. Okay, thank you.
Have to be superimposable in that case.
Okay, thank you.
Because they are the same molecule. So they surely can, which is like talking about you're taking the same molecule, right? And then you just try to stack on it. It's the same thing. So it will be superimposable. Yeah.
Okay, thank you.
Yeah. I think we borrow to you. Yeah, I think you did it again. Oh yeah.
Correct.
No more idea. Okay. If you build the mirror image, right, it's gonna be like that. This is a mirror image. But then instead, you see it's like superimposable. It does the same thing. Yeah, because the reason is because there's a plane of symmetry. Okay, 3.3, last section. Very fast, yeah. Okay, this section will deal with conventions for representing these three-dimensional lattices. Construct model for a pair of enantiomer using tetrahedral covers of 4 different color components for 4 different groups. Okay. Okay, this is basically another way to represent a 3D models. Yeah. Okay. Later this one, give back the link. Back. Later. Yeah, you use first. You use the problem. Just that I don't mix with that box. Okay, this one is basically a different way of representing the 3D model into 2D. Okay, so this one you are using a wedge and a dash line. Okay, so you can see from here, you use a wedge or a dash line. Yeah, so you can see from here. Okay, if you use the wedge type, okay, it's pointing towards you. If you use the line one, it's pointing away from you. Okay, so imagine that this one is the plane. Okay, this one is the plane. If you do a dash line, right? Okay, if you do a not dash line, if you do a wedge one, which means that the molecule is pointing towards you. Okay, if you are doing the dash line, means you're going away from you. Okay, so there's use this as a plane. Okay. Okay, do you have the model?
Not yet. Oh,
Okay, so you can imagine that. All right. So if these two is a wedge, okay, if these two are the wedge, so what happens is that this is the plane, Okay, so if this is the plane, it means that you are pointing towards you, and this one is away from you, these two. Okay, these two means it's behind the plane. These two, the orange and the yellow, is the in front of the plane. Okay, so this is the plane. Okay, not aeroplane. Okay, so this is the plane. All right, behind plane, in front of plane. Okay, so you the in front of plane one, then you use the wedge to do it. The one with the this one. This is called wedge. This one is the dotted one. Is to represent the one pointing behind. Okay, so in using this wedge and the dash line, right, you can represent a 3D molecule into a 2D. Okay, you can know where it's pointing. Okay, and here. Oh, yeah. So this is the, imagine it's a molecule, right? So this is the plane. Okay, this is the plane. So if these two, you can see the orange and the yellow is pointing towards me, right? So you use the wedge. To represent, yeah, the wedge is yes. And these two behind the gray and the green is away, right? So you use the dash. Yeah. Okay. If it's line like that, if you're doing a line like that, okay, if you are doing a line like that, these two will be a straight line. Okay, guys, if you want to do like that, yeah, if in this case only the yellow is pointing front, the green one is pointing behind, okay, then this the gray and the orange is in plane, it's called in plane, so you just draw a line only, okay, and this one will be dot 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 dot, and this one will be the wedge, and these two will be a straight line. Okay. Yeah, this one is called the dash line wedge. Yeah. Okay. That's it already, is it? Finish it. No. Come on. Okay, that's it. Finish. No wonder you are like starting to keep already. Combine these two. Yeah, very good. Okay. Okay. Any question from inside? On the dash and line? Silent means no question. Show thumbs up there. Show that you're still there. Thumbs up. Wait, I see one thumbs up. Anyone else? Sorry, depends on how you orient the movement. Yes, correct. The dash one will be the dash one. So these two will be back. These one are two facing away like this. Yes, and this one facing. This one is facing. Yes, these two are facing behind. Yeah. But in this case, you just put this one. You can just put it in a straight line because it's just facing up. Yeah, if it's in plane, then you don't need to dash and wedge. You just going up. Why got people still enjoy? Yeah, if it's like that, just one line, just a one line. If you do like that in plane, so this one will line. This one will be the dash. This one will be the wedge. It's a different way of okay. Is this
so can you show the dash line wedge again?
Dash line wedge. So it depends on how we. Yes, depending on how you. Okay, depending on how you view it, that's how you do it. Which one you're not? Which one?
The dash line wedge.
Certain model.
Wait,
Right.
yes. Yeah. You see over here? Green, orange, gray, and the yellow, yeah. So this is how you have it. So if you are wedge, you are actually, this is just say that this is a plane, yeah. Okay, so if you look at the side, this one will be the plane. Okay, yeah.
Okay.
Gray.
Green is
Yeah, yeah. Okay, like that. This is the plane. Okay, this is the plane. So this one plane, this one is pointing towards me. Okay, so if I'm in front here, okay, if I'm in front here, this one will, the gray and the yellow will be pointing towards me, and the green and the orange will be away from me. Okay, so this is the plane. Okay, so this is the in front of the plane. This one is behind of the plane. All right. So in order for you to represent in front of the plane, okay, by having the gray and the yellow pointing you draw a wedge. The yellow and the gray is away from you, you draw a dash line. Okay, so this is supposed to be like that. Okay, you can see this one is behind. So this one pointing towards you, you draw a wedge. This one away from you, draw a dash line.
Oh, all right. Okay, I got it now. All right, sure. Thank you. Yes.
Say that these two, if just say these two is in the plane, okay, and only this one facing you, this one facing back, then this one will just a straight line only. Draw a straight line. Then this one is a wedge, this one is a dotted line.
A straight line means that it looks like the Fisher projection, right?
No, if it's straight line means in plane, which means in
Oh.
the plane. Yeah. Which means in the plane. Okay? In plane.
Right.
Okay? Yeah.
How about for the Fisher projection? How should we imagine it?
Fisher is just a line only.
Oh,
Yeah, Fisher is just a line only. Sorry, Fisher is only line only.
okay, thank you.
Sorry, yeah. You are showing my body only. Nothing to see. Okay. Okay. You want this? Okay. Okay. Any more questions? No more questions, then we end here. Lah. The lady behind me already so ready to go already. Okay, any more questions? Yeah, no question. Okay, then, okay. So anyone want to say bye-bye?
Bye.
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 Bye, everyone.
Bye.
Bye.
Thank you, Dr. Ben.
Thank you, Dr. Ben. Goodbye.
I'm so envy.
See you tomorrow. No, the Technology 101 is in online base. Yeah. So see you on Wednesday. Yeah. Okay.
Okay.
Bye.
Thank you, Dr. Ben.
Thank you,
Bye,
Dr. Ben.
guys. You did a great job.
Is it?
Oh, this one to circle.
The circle and the what?
Sure. Okay, I'll just sponsor that.
Just catch paper.
Yeah.